All right, it's time for LeetCode Weekly Contest 188. Okay, so I'm done with the contest, and I've thought about the problems and actually written solutions. So hopefully these explanations will be better. Also, I finished the last problem in exactly 1 minute 29:26. So that's pretty impressive, and I was super happy when I solved it. So the first problem is build an array with stack operations. I was pretty confused by this one. Um, But like if you read the problem statement, it kind of starts to make sense. So I'll explain the problem in a better way. So you start out with an empty array, and given n iterations, um, in which each iteration you can either choose to push or pop. During the ith iteration, starting from 1, if you push, you add I to the end of the array, and if you pop, you delete the last element of the array. You want to eventually construct the target array, which is given. For example, it's 1, 3, 1, 2, 3, 1, 2, 2, 3, 4 over here in the examples. Um, and it is increasing. So its max element is at most n. So you want to return the sequence of push and pop operations which can construct the target array. This is not a hard problem to code, but basically it's very useful that the target array is already sorted. So we keep an index which keeps track of which value in the target array we want to append to the original array next. And during the ith iteration, if I is the next value we want to append, then we add push to the sequence. If I is not the next value, then we do push then pop to essentially do nothing. And since the target array is increasing, we can disregard the number x once we've gone past the x iteration. And if you don't understand this, don't worry, it's kind of a confusing problem, and I had to read this multiple times before I could solve this too. Problem 2, count triplets that can form two arrays of equal... Okay, so apparently it's XOR. Okay, you are given an array of integers, and you want to select three indices I, j, and k, where I is less than j and j is less than or equal to k, such that these two numbers a and b are equal. So we are given that a is the XOR of all elements between indexes I and j minus 1 inclusive, and b is the XOR of all elements with index between j and k inclusive. We want to find the number of triplets where a equals b, and the constraints are such that the array's length is at most 300, and 300 choose 3 is about 4 million, I think. I don't want to get that wrong again. Remember and 300 choose 3 is about 4 million. So we can do it in enough time if we keep this constant other than the 300 choose 3 part. But essentially what we do is we construct a prefix table for the XOR. And basically what this means is we have the ith element is the XOR of all the elements in the array up to index I. And this is useful because if we want to find the XOR of a certain interval, we can just take the prefix table value of the end, XOR that with the prefix table value of the start element, and that can give us the XOR of the interval, because that's how XOR works. You know, it's kind of a special function. Then we can just straight bash all the possible triplets, like using this for loop, and we can calculate a and b in constant time because we have this prefix table, and we can use the method that we described previously. And then if a and b are equal, then we increment the count, and yeah, we just do that. Oh, also one note, I tried this with Python first, but apparently Python was too slow, so we can see here. But with Java, it actually works. So yeah, see, Python doesn't work, but Java works. And I saw this previously on an XOR problem. You can watch the previous videos. I don't know which one it is. I can probably find out. But yeah, it doesn't work with Python, but it works with Java, which happened before. So yeah. Okay, problem 3. Minimum time to collect all apples in a tree. You are given an undirected tree consisting of n vertices numbered from 0 to n minus 1, which has some apples in their vertices. Okay, finally, they're indexing from 0. You spend 1 second to walk over one edge of the tree. Return the minimum time in seconds you have to spend in order to collect all apples in the tree starting at vertex 0 and coming back to this vertex. So basically, some of the nodes in this tree are apples, and we have to do a walk over the tree, and you can repeat edges such that you visit all the apples. We are given this table as a list of edges, and that's not very convenient, so first thing we do is to convert that into an adjacency list. So basically, for every node, we list all its neighbors. Yeah, and then we can have a recursive function which takes in a node and its parent node, and even though it's undirected, we still have parents because actually, no, that's not true. But if you specify a root node, you can derive the parent property. Kind of important to note that this is not a binary tree, so you can't just have 2 children for every parent. Like, it doesn't work that way. That's why we have to create the adjacency list. So basically, this recursive function takes in a node and the parent that calls the node. And we look at all its neighbors, and then for each neighbor, we calculate the time it takes to travel to all its apples. And if a neighbor does have apples, then we need to travel to that neighbor, collect all the apples, and then come back. So we actually need to add 2 to the value of the time that it takes to get all the apples there. But if the neighbor has no apples in its subtree, then we don't even need to go to the neighbor because there's no apples over there. So we can just do 0. But otherwise, we do 2 plus the time it takes to get there. And then after all the neighbors have been visited and we total everything up, we look at the amount of time it takes for the original node. And if it's 0, that means it has no apples in its subtrees. And that means we can return -1 to signal that it has no apples there and like its parent doesn't need to go there. Otherwise, we can return 0 if itself is an apple, but none of its neighbors has an apple, because, you know, we still need to go there to collect it. Yeah, in the end, we just call this function on the original node. And yeah, we don't have to specify a parent. Yeah. Okay, problem 4. Number of ways of cutting a pizza. Given a rectangular pizza represented as a rows times columns matrix containing the following characters A and empty cell, and given the integer k, you have to cut the pizza into k slices using k minus 1 cuts. So It's kind of better to understand this if you can see these pictures. But basically, you make straight cuts along the grid of the pizza, which is like a rectangle, and then you can remove the top piece or the left piece every time you cut. If you cut vertically, you remove the left piece, and if you cut horizontally, you remove the top piece. Every time you make a cut, the piece that you remove has to contain at least one apple, and you do this. You make k-1 cuts to create k slices, and each slice must have at least one apple, right? The solution, I think there's a better way of doing this using dynamic programming. I basically did dynamic programming, except a dumb way of doing it. So it's not as efficient as it could be, but it got the job done. So at first, I tried recursion, which was too slow. And then in the last minute, I just added on the dynamic programming table and the inefficient one. And yeah, it actually got accepted. So I'm happy about that. First, we initialize the DP table, which actually accepts 4 values. It should only accept 3, but the recursion function originally used 4. So we just made it 4 to make it convenient. And the recursion function accepts 4 parameters. It accepts the top left coordinates because every subslice can only contain the cells to the right and down because we always remove the top and left. So we are only left with the right and down. So yeah, specifying the top left coordinate can give us the entire sub pizza. And then k is the number of slices we have left to make, and remaining apples is the number of apples that are on this slice. So I'm going to use this one as an example. Basically, it's a 3x3 grid. There are apples in the top left, one below the top left, in the very center, and one to the right of the center. The sub pizza we're going to use is the bottom 2x3 rectangle. K would be 2 because we originally started with 3, and the number of remaining apples is 3. What we do with the recursion function is first, if it's already computed in the DP table, then we just use it. Otherwise, the base case is k equals 1, which means that there's only one slice left to make. And in that case, if there are any apples left at all on the slice, then we can return 1 because there's one way to do it, which is just to leave it as is. But if it does not have any apples left on it, then we can't return it because every slice must have at least one apple. So we return 0 in that case. Otherwise, if k is not 1, if we have to make more slices, then we can either make horizontal or vertical slices. And each of those is essentially the same because, you can like rotate it and like it's symmetrical, right? So let's assume you have a vertical slice. And if you do a vertical slice, then we increment through the columns in which you do the vertical slice because the vertical slice goes through a certain column. Yeah, we go rightwards, column by column, and we keep a count of how many apples are removed by the cut starting at 0. Every time we increment the row's index, we take a look at how many apples are in the row we just removed, and we add it to the total remove count. So for example, if we're starting here, then remove count would be 1, and then if we move it here, then the remove count would be 2. And this is important because we need to make sure the number of apples we removed is greater than 0, and only in that case can the cut be made, because each slice must have at least one apple. But we also need to make sure that the apples that are left are enough to spread among the remaining slices. So since we're making k-1 additional slices after this cut, we need to make sure there's at least k-1 apples remaining after our cut. That is why the remaining apples parameter is important, because we can subtract the removed apples from the remaining apples to calculate how many apples will be left after our cut. Once we do that, we loop through all the possible vertical cuts. We stop once we've hit a number of remaining apples after the cut that are not enough to spread among the remaining slices after that. And yeah, we just total it up. And then we also do it horizontally, which is the same thing. And then at the very end, we record it in the DP table, and then we return it. At the very, very end, we calculate how many apples there are in the entire pizza, and then we just use 0, 0, k, and then total apples. This was, I had a lot of off by 1 errors, which were not very nice because, they just made me frustrated, and I had to do a lot of print statements. But eventually I got it sorted out, and it was too slow because it didn't have the DP table. And then I put the DP table in, in the last minute, and it worked. So yeah, it's getting late, and I guess I could rant about some of this stuff. No, I'm not going to rant. But this contest was a good contest. Hopefully the Yuzuko video is going to come soon. I'm not sure when I'm actually going to have time to do it, but probably once school ends, I will be able to do it. This was a fun contest, and I hope you enjoyed my explanations as well as the video. So if you have any feedback for me, just please leave it in the comments. Thanks for watching. Goodbye.